Okay, so where we left off, you just took the inverse log of 0.6, and you should get something like 3.91807. On this side, the inverse log and the log cancel each other out, and you're just left with I over IO. You're trying to solve for I, so multiply both sides by IO. So 3.98107 times IO, which is the constant, right? This is IO up here. So 1 times 10 to the negative 12. So I is equal to that 3.98107 times 1 times 10 to the negative 12 watts per meter squared. And when you multiply those out, you get 3.98107 times 10 to the negative 12 watts per meter squared. Okay? So there's two different examples of how to use that equation. All right, continuing on. Flip the page over from loudness. And now we're going to talk about frequency. We've already talked about frequency before. We know that in sound, frequency is pitch. And so for those of you that are musically inclined at all, you probably already know a lot about frequency. Whoops, it'd be good if I had an E in there. Okay, so changing the frequency, you're really just changing the pitch. If you think of in strings, like guitar strings, there are 3 different ways, if you play a stringed instrument, that you can change the pitch of your string. One way is what? Stop and think about it. Well, one of the things they do is they put their fingers on different frets, and by doing that, they're changing the length of the string. Changing the length of the string will change the frequency with which it vibrates. The longer the string, the lower the pitch. Okay, so that's one way. Another way, if you've ever looked at a guitar, is that you would notice that the strings are different thicknesses all the way, up or down. They start thin on top and they go thick on bottom, I think, usually. So a second way to change the pitch of a string is by changing the thickness. And the thicker the string, the lower the pitch. The thinner the string, the higher the pitch. It's actually why adult males tend to have deeper voices than adult females, because just like everywhere else, they have more muscle on their vocal cords, so it's a thicker string, and so the pitch is lower. Okay? The third way to change the pitch in a string is to change the tension. And again, on a stringed instrument like a guitar, you'll often see people changing the pitch by adjusting the little knobs at the top. They're tightening or loosening the string. The higher the tension, so an increase in tension, is going to do what, do you think? Yeah, it should increase the pitch. And actually, that's how I change my pitch in my vocal cords. I just increase the tension in there. I don't know how to go the other way and decrease it to make it deeper, but I can make it higher. Okay, so that's in strings. Now, our ear can only hear certain pitches. We can only hear frequencies from 20 hertz up to 20,000 hertz. For us, this is the audible range. Okay? Anything below 20 hertz is below what we can hear, and it's called infrasonic. Any sounds down here are infrasonic. We might feel them. We might feel them down here, but we can't actually hear them. We might feel them as vibrations. Anything above this range is called ultrasonic, and a number of you have probably experienced ultrasonic sounds because we use ultrasonic sounds in medicine. You go for an ultrasound, and they shoot these waves into your body. They reflect off your different organs. They come back, and they put the image together to see what's going on inside. Okay, but it's just sound waves they're doing. Animals can hear higher than 20,000 hertz. Our dogs can. Our cats can. Okay, or not our cats. Sorry, my iPad was just doing something weird. Our dogs can, dolphins can, bats can. They can all hear up here. But the majority of us, this is stereotypical, hear between this range. Now, as we get older, we lose our upper range. Actually, for most of you, you can probably hear higher than this. You can probably hear up to maybe even 30,000 as young people, and then as we age, it drops down. This is where something that's known as the mosquito ringtone comes in, and I'll talk to you about it tomorrow, but it's a high-pitched sound that it was believed that young people could hear and older people couldn't. But remember, this is stereotypical, so tomorrow we'll find out how many of you can hear it. But it goes to a really neat story that I'll tell you tomorrow. So for most of us, this is the audible range. Every vibrating object produces a sound. So I'm vibrating this pen back and forth right now. It's producing a sound, but unless it's going more than 20 times a second, we wouldn't be able to hear it. Okay, it has to be more, it has to fall in the audible range. So I'd have to get it going pretty good to do more than 20 times a second. Okay, so that's the audible range. And tomorrow we'll do something to see what your audible range is. Last thing under pitch that I wanted to talk about was in music again, different vibrating, and all our musical instruments, they're really just different things vibrating. So if we look at drums or cymbals or even our vocal cords, what's vibrating is the instrument itself. In things like trumpets, trombones, tuba, what are vibrating there, these are the brass instruments, it's our lips. In reed instruments like clarinets, saxophones, and oboes, there's a tiny little thin strip of wood called a reed that vibrates when the air blows across it. That's the word reed instrument. Wind instruments, flutes, recorders, organ pipes, whistles, what's vibrating there? The actual air itself. And then stringed instruments, guitars, violins, and even pianos, what are vibrating there are the strings. Okay, so every vibrating object produces a sound. It's just whether or not that's in the range we can hear. And the last note here, for brass instruments and reeds, the mouthpiece alone isn't enough. And so oftentimes we'll move like the air column, change the length of the air column to allow for more vibration. And we'll get into air columns vibrating before too long. Okay? Two more little things. I think I might have time enough to do, whoops, got that one. Beats first. So you have to flip over 2 pages to beats. Okay, beats are something, again, that you might hear in music, and those of you musical might even use them to tune your instruments. Beats are a result of interference. And I could try to draw pictures, but probably the best bet is to show you in the textbook. So in the textbook on page 429, let me see if I can get it focused here. Sorry about making you seasick. All right, in 429, it shows us 2 waves. This top wave has a frequency of 10 hertz, and the lower wave has a frequency of 12 hertz. They're really close together in frequency. If we were to add these together, we get the red one at the bottom. See, notice at the beginning, they're totally out of phase. Then, as time goes on, they move into phase. Like so, right here on this dotted line, they're in phase. So out of phase would mean the resultant has very little amplitude. In phase means the amplitude will be big. But then they go out of phase again. And then they go back in phase. So what the red one shows us are the beats that are a result of these 2 waves interfering. The sound goes loud, then low, loud, then low. There are 2 beats here, which just happens to be the difference between the frequency of these 2 waves, the 10 and the 12 hertz. Okay, so if we go back to your page on beats, it says constructive, whoops, let me just zoom out a little. Constructive interference produces louder sound and destructive quieter sound. So that's when you hear the beats. How do you find them? You just subtract the 2 frequencies, F1 and F2, to get the beat frequency. These straight lines mean it's always going to be positive, so it doesn't matter which one you take away from which. Or if we knew there was something like 7 beats, maybe